My name is Carlo Giacometti, and in this talk I will cover the new capabilities of the Wolfram language at the intersection between neural networks and audio processing. So my name is Carlo Giacometti, and today I will talk about neural networks for audio, mainly analysis, I would say. So the first thing that I want to show that has been updated in 12 is the audio net encoders. So encoders are the entry point for data onto the world of neural networks. These were introduced, as I said, in last version, 11.3, and they allow very fast and parallel feature extraction from audio, both objects and files. Several different features can be computed using net encoders. And I will very quickly go through them. One is just a plain waveform. The short-time Fourier transform can be computed. The spectrogram, the MEL spectrogram, which is very similar, just with a more human-friendly frequency scale, and the MEL frequency cepstral coefficients. So this already existed in 11.3. It has just been made more efficient and faster. Another thing that has been added to the audio encoders is augmentation. So if you have a limited amount of data, you really want to trick the network into believing that it is seeing a more varied distribution of data. And many times, this kind of augmentation needs to happen before the feature extraction process. And this is why we have included it in the encoders. One example of augmentation that could happen is shifting the time of the input signal. So, and this can be randomized according to a distribution that can be specified by the user. You can see here the two different inputs have different starting point. And this can happen at training time online. Noise can be added to the input to make the network more robust to different kinds of signals. So the noise can be automatically computed as white noise, but you can also compute or generate a noise signal. In this case, this is just an annoying story about that. But if you have on your machine a collection of noise samples that are representative of the real-world data that your network will see, this is an extremely useful augmentation for your network. Convolution just convolves the signal with some impulse response and simulates the presence of different kinds of reverberation. So all of this is useful to prepare the network to signals that are not really in your training set, to allow the network to generalize better to different kinds of data. Does it really help? Is it really useful? So here I have the spoken digits commands dataset that has a collection of digits spoken by various people. And what I have done here is training the same network, same parameters. The only difference is that one encoder has no augmentation, and the other one adds noise randomly to the input. And as I said, I am limited the amount of data that I'm exposing to the network. And both trainings succeed and converge, and you can compare the two results. One standard measure is the accuracy, and you can see that even in this very much toy example, we get a 2% absolute boost on the accuracy of the result. Of course, it really very much depends on the kind of problem that you're trying to solve. But this is definitely a very valuable addition to our framework. Another new thing in version 12 is audio identify. What does it do? It takes a signal, in this case, this one. Okay. It was not as annoying as the previous one. And it tries to figure out what are the contents of it. You can specify, you can restrict the search on a limited set of categories. You can return multiple results. You can return the probability, well, the score of those results. And of course, everything here is based on a neural network that users can access using the net model. At the moment, it is still hidden in our repository, but we are planning to make it public when we have a final version. This, though, is accessible by anyone. It just says hidden in the name, but it is definitely accessible. So we did the training of this network in-house. How does it work? What was it trained on? We used the audio set, which is a data set that was released by Google that contains a couple of millions of audio snippets that are labeled with a collection of 632 audio event classes. These are some examples of classes. You can see human sounds, voice, etc., etc. These classes can be represented with sound entities in the Wolfram language, and you can even gather a description out of them. Now, these classes are organized in an ontology, so there are some hierarchical relationships between the various classes that can be accessed with this nice private function. As you can see, it is a messy graph. It is a messy graph. And it has some issues. As you can see, some of the classes have multiple parents, which leads to problems in scoring the results. But this is how the dataset was released, and this is what we have used. One very important characteristic of the data is that it is inherently multi-label. So for one single sound, that can be assigned multiple labels. So for example, there is in the song or in the recording, there's a guitar, but there's also a person speaking or an electric piano or something. Both of those labels are present in the training set. So we're not doing a classification where the classes are mutually exclusive. It is a multi-label classification, which is a very different problem. As you can see, this is one example of the raw training data. These refer to the audio files, and these are some representation of 3 classes. So this segment contains all of these 3 classes. So how does the training work in this weird multi-label setting? What ends up happening is that you need a separate classifier per each class. And this is done by specifying that at the end of the classification layer, the nonlinearity used is logistic sigmoid applied independently to each of the inputs, rather than a softmax layer which would represent the mutually exclusive probability case. And then, of course, the result of these independent classifiers is passed to a cross-entropy loss that is then averaged over all the classes. So this is how the data was structured. What is the network? Well, we can inspect it very easily. Well, this looks very long. The architecture is called MobileNet version 2. The inspiration for the architecture was taken by this paper, but we end up using a more modern architecture. This is MobileNet version 2 is a convolutional neural network that is generally used for image processing. Now, image processing network, the input is of a fixed size. Audio is inherently a variable size. So how do we connect these 2 worlds? Well, we connect these 2 worlds by massaging the output of our encoder. So we can extract our encoder and see what it does. As you can see, the crucial operation here, after a MEL spectrogram is extracted, so you have a variable length matrix, this variable length matrix is then partitioned on a sequence of fixed dimension intervals. This way, we can map the fixed length neural network onto each of these chunks. And let's see. So this is the result of the encoder. As I said, we can use net map operator to apply the net onto every single one of these chunks. And this gives us, in this case, this result. In this case, the number of chunks that we have extracted is 2, so we get 2 classifications. But we really want to have one single output per audio signal. So we need to aggregate along the time dimension. We cannot really use the average, since we don't want to know what the average sound was. We really want to know what sounds were played. So we use an aggregation layer where the aggregation function is max. So this way we collapse the time dimension and get a single result. This is the result. And once we have this result, we pass this to the decoder that knows about which classes are in the training data, and this can give us a series of probabilities. So this is the raw network. In audio identify, we take also into consideration information from the ontology to score the result. Again, this is the big messy graph from the ontology. And we can, from audio identify, we can control how much information from the ontology is used to score the result by the specificity goal option. In this case, we can give more or less weight to elements that are closer to the branches of this graph rather than the center. And you can see the generality of the result. Here I am mapping over values from 0 to 1. And you can see the first result is acoustic guitar. The result from specificity goal goes to 1 is just music. So it's also possible to run it in real time dynamically. In this case, I have this. I just made quickly this audio object by joining all of our audio data. I am creating an audio stream and playing it.
You will return safely to Earth.
Hopefully you can hear it. And now I will run audio identify in real time on the signal from this stream. And it can be also a stream from the microphone. And we have some demos in the basement where you can experiment with this if you are so inclined. Let me delete this effort. So this is audio identify. Now, sure, figuring out what instruments or what sound sources are in an audio signal is interesting, but it doesn't have many super practical applications. But one important thing that we can get out of this trained network is semantically significant feature extraction. So what we can do is chop off the last few layers of the network that are in charge of the classification. And this is what I'm doing here. What this produces is, okay, there is some issue here. What this produces is a fixed length vector that is semantically meaningful with respect to the content of the audio signal. So here I am collecting all of our example data, and then I am trying to do feature space plot of our example data by specifying that the feature extractor to be used is the network that we just produced. And you can see that there is, so these are all the various audio objects. You can see the spectrum, but you can also
You will return safely to Earth.
That's one small.
And you can see that similar signals are clustered together. And it is, so this is a more concrete application for the network. How do you find out if two signals are semantically similar. This is one way. You compute features from them, and you compare the features in their feature space. And by the way, now we have included the network that we're using as the default feature extractor for all of the machine learning functionality. Say feature extract, feature space plot, classify, predict. So now if you do feature space plot of a list of audio objects, that network is automatically used. And as you can see, you still get semantic separation of clusters. Now, another use of the network, it can be used as a starting point for doing more specific problems. The one that I'm showcasing here is very simple. We have a data set that is called IRMAS that contains a collection of audio snippets of various instruments, and the instruments are labeled. Let's see. This file, for example, contains organ, and et cetera, or a flute. There are only 11 available classes. But if you had to train a neural network from scratch to distinguish from all of these classes, that would be a fairly resource-intensive process. And probably would get a reasonably bad result because the amount of data is fairly limited. It's, I think, only a few thousand examples compared, for example, to the data set that we use for audio identify, which is a couple of million of examples. So we are kind of cheating the system and using the feature extraction from the audio identify net as a starting point for this classification. So the problem is not anymore to classify an audio object into 11 classes, but the problem is I want to classify a vector of length about 1,000 into 11 classes, which is much more manageable. So here I am using just classify, and I have pre-encoded the data just for practical purposes. I will not run the computation. It takes about 3 minutes, but I don't have that much time. So, and then you can easily look at the classifier measurements of the result. And you can see with limited data, limited time, very limited resources, I still get a 91% accuracy on the data set. Now, this was the kind of lazy approach. We left classify to do all the work. But we can start from the same starting point, the extracted features, and train a small neural network, a small classifier neural network from scratch. As you can see, the net is essentially 2 linear layers with the respective non-linearities. That's it. And as an input, it gets the, is everything okay? Yes. Yes, so as I said, a few classifier layers, and that's it. And we can see how long it actually takes to train. Let's see what we get. Oh, I think there is some issue actually. This does not look too promising. Okay, I will use the pre-computer result just to let me check if everything, yes, that is definitely not giving me this nice result. Okay, so evidently I used some slightly different hyperparameters earlier. I'm not getting the same result, but with a very tiny fully connected network of just, in this case, 3 layers, I can get a 95% accuracy on, as I said, our very limited in resources data set. And with this, we can create, by joining the network that we use, that feature extractor, with the network that we just trained, we can create a full net that takes an audio object as an input, extracts the features, and then classifies it. And let's grab a random example from the instrument dataset. And this does the classification from audio object to, in this case, one of 11 instrument classes. And it just works. And this is the magic of transfer learning. You use a network that was pre-trained for a similar but different, but not the exact same task. And you retrain the last few layers that are in charge of the classification. That this reduces greatly the resources needed to be successful at that kind of project. Another new function that was introduced in 12 is pitch recognize. So there are several, the goal of the function is to figure out what the pitch of a monophonic signal is. And by monophonic, I mean only one source was playing at a time. So in this case, I will have a piano signal. Let me play that for you. So, of course, there are very valid classic signal processing algorithms that can be applied to this that do not use machine learning at all. That is the default method used in pitch recognize. But if you want more precision at the cost of definitely a longer evaluation time, you can use a different method in the function that calls a neural network. And it's evaluating now, and this is the nice result. The interesting thing is that the backend of this function is a network that is present in the neural net, Wolfram neural net repository, and it's called CREEP. Here we go. This network acts on the raw waveform of the signal that is then partitioned and classifies that signal onto a collection of one of 360 pitch classes. So these are pitch classes. It's not a frequency. We need to transform it to a frequency. There are several choices that range from a simple interpolation to using a hidden Markov process to have a cleaner decoding. So we can compute the result of the network. And it will take a little bit of time because, as I said, it's... And this really depends on your machine. If you are able to evaluate this on a machine with a compatible GPU, it will be, of course, much faster. We can use the hidden Markov process to decode the result. And this whole process gives us both the prediction of the pitch, but also gives us a prediction of the confidence of our result. And we can visualize this result. Here, the color, the opacity of the line in this plot is related to the confidence of our result. And this is how the neural network backend of pitch recognize works. Thank you very much. This is the team that works on signal processing, and thank you again.